Hi everyone, I'm Tegan Brennan, a PhD candidate from the University of California, Santa Barbara. Today I'll be presenting joint work with Nicholas Rosner and Tefik Bolton on inducing timing channels through just-in-time compilation. Traditionally, side channel vulnerabilities in software are caused by an observable imbalance in resource usage across different program paths. In the equals function shown here, two strings, a guess and a stored password, are compared character by character. As soon as a mismatch is detected, the function returns early. This early return introduces a timing side channel that allows an observer to determine how many characters of their guess match the stored password. The two violin plots on the right illustrate this side channel. The blue violin plot shows the execution time distribution of the equals function when it's run on input whose first character does not match that of the password. The width of the violin plot shows the number of program runs that fall into that execution time bucket. The violin plot in green shows the execution time behavior of the program when run on input whose first character does match that of the password. These two execution time distributions are distinguishable. In fact, they can be separated quite accurately by a simple line. This means that a timing channel exists in this program, allowing an observer to determine whether or not the first character of their input matches that of the password. Of course, the magnitude of the time difference here is in nanoseconds, so whether or not this would be observable to an outsider is another concern. But at least theoretically, this side channel exists. Now, that side channel was caused by the early return in the equals function. So, to fix the vulnerability, we might think, well, let's remove the early return and instead ensure that an equal amount of work is done, regardless of whether or not the characters match. As a result, a developer might end up with the new equals function shown here. Well, problem solved? We don't have to guess. We can experiment to determine whether or not this is the case. Here, we see the results of the same experiments run on this new version of the equals function. Again, the violin plot shown in blue gives the execution time distribution of the program when run on input whose first character does not match that of the password. The violin plot in green gives the execution time distribution when it does match. Now we see a much different story than before. These two execution time distributions seem pretty indistinguishable. So, have we really solved the problem? Well, there was one crucial bit of information I kept from you when running those experiments. That data was collected with just-in-time compilation disabled. The key insight behind our work is that runtime behavior, in particular just-in-time compilation, can actually introduce timing channels into programs, even those that appear to be side channel free at the source code level. Just-in-time compilation attempts to optimize paths it deems hot, and in doing so can introduce timing side channels, allowing observers to learn predicates related to branch conditions. Knowing this, let's return to our experiment and see what happens when JIT is enabled. As you can see, the story has now completely changed. Now the execution time behavior given by the blue violin plot, that when the characters do not match, is markedly different from that given by the green violin plot, which is when they do. The reason why is because I ran this program with randomly generated input. This made it much more likely that the first two characters do not match. So JIT optimized for that particular program behavior, introducing the side channel that we see here. Throughout the rest of this talk, we will be discussing three different components of these JIT-induced side channels. We'll first discuss in what kinds of environments JIT-based side channels can arise, then what kind of information we can learn through these side channels, and finally, a systemic strategy for exploiting JIT-based side channels. First, Let's consider an example of the kind of environment where JIT-based side channels may occur. We could have some application allowing different types of login. A low privilege login, which occurs frequently and is the common behavior of the application, or a high privilege login, which only occurs rarely. Through a JIT-induced side channel, some user executing only their low-level login privileges can actually learn if and when a high-level login happens. This is an example of one of the 3 attack models we introduce in our work. It is an example of the natural priming to learn atypical behavior model. In this attack model, there is some natural bias in the system towards a particular program behavior. In our example, the bias was towards the more common low-level logins. The observer is able to learn if and when atypical behavior, in our example, a high-level login, occurs. They are able to learn this through the timing of their own probes, which are instances of the system's typical behavior. The next attack model is the natural priming to learn typical behavior model. Here, once again, there is some natural bias in the behavior of the system, but this time, as an outsider, we are unsure as to the direction of the bias. As an example, consider a voting platform where users have a choice between A and B. There is some bias towards one of these choices, but we are unsure as to the favored choice and can use JIT-based side channels to learn this. The final attack model is the induced priming model. We will be using this model as part of a running example, so we take a moment to introduce it in context of that example. Under the induced priming attack model, the attacker has enough control of the runtime to effectively booby-trap the runtime to prefer a particular program behavior. Here, we have a short code snippet that determines if some input is less than or equal to 50. The attacker would first prime the runtime by sending many requests, all of which agree on this predicate and are less than or equal to 50. This primes the runtime to favor that program behavior. Then, when some other user makes a call using unknown input, the attacker can tell, based on the timing information of that call, whether or not that user's input also satisfies the predicate and is less than or equal to 50. The second aspect of JIT-based side channels we want to discuss is what can be learned from them and how that relates to the program's source code. From our initial password checking example, you probably already have the intuition that what is being learned via a JIT-based side channel are predicates over input relating to branch conditions in the source code. From this intuition, I developed 5 vulnerability templates to determine how particular source code fragments might be vulnerable to JIT-based side channels. Each template consists of the JIT optimization responsible for the side channel, a code pattern describing how the branch condition must appear in the source code, and a recipe for how the runtime must be primed for the side channel to be induced. Of the JIT optimizations considered, I think the optimistic compilation template is the one most likely to be unfamiliar, so I will spend a moment introducing it. For the optimistic compilation template to apply, the function or code segment in question must be deemed very hot and be aggressively compiled. If the dynamic profiling gathered before compilation deems that one evaluation of the branch is very rare, then the function will actually be compiled with that branch removed. If and when the optimistic assumption that that branch is never taken is broken, the runtime must then revert to a less optimized version of the code. We now turn to our final question. How can you exploit JIT-based side channels? Using a profiling strategy provided by the attack model and profiling parameters given by the vulnerability template, we developed a 2-stage approach to effectively use JIT-based side channels to learn predicates over input. The first stage of our approach is the profiling stage. In this stage, we gather information about execution time distributions that will later allow us to make accurate inferences. The structure of the profiling stage depends on the attack model in question, and we show here the profiling stage for the induced priming attack model. First, the attacker primes the runtime to favor a particular program behavior. For example, to favor input that is less than or equal to 50. Then, the attacker generates some input that agrees with their priming of the runtime. The attacker will then time the execution of the program on that input. The attacker will then repeat this priming timing process, timing the execution of the program on new input, also satisfying the predicate of less than or equal to 50 each time. The end result will be an execution time distribution of the program's behavior under a primed runtime for input that satisfies the predicate. Then, the attacker will gather timing information for the other case, when the input does not satisfy the predicate. The attacker will prime the runtime just as before. Then, the attacker will time the execution of the program on some input not satisfying the predicate. The attacker will repeat this process, and the end result will be an execution time distribution of the program's behavior under a primed runtime for input that does not satisfy the predicate. With this profiling stage complete, the attacker can then turn to inference. In the inference stage, the attacker primes as usual. Then, the attacker times the execution of the program on some real victim's unknown input. The attacker then determines which of the two execution time distributions collected during the profiling stage the observed timing information more closely matches. Based on whether it more closely matches the case where the input satisfies the predicate or the case where the input does not satisfy the predicate, the attacker can infer the value of the predicate on this unknown data. This completes our profiling and inference strategy. We now discuss our results in inducing JIT-based side channels on 4 case studies. The first case study is on the Apache Shiro security framework. This case study closely resembles our early example with high and low level logins. We used the tutorial code available on the Apache Shiro site for this example. We assumed that low-level logins are much more common and began our experiment by having many low-level users authenticate themselves. Then we began probing the system with our own low-level logins and timing those calls. After 100 probes, we had some other high-level user log in, but we did not time that call. Then we continued probing the system and timing those probes. As you can see here, the timing behavior of our probes changed noticeably right after the high-level login happened. To determine whether this was really because of the atypical high-level login and not some other aspect of our experiments, we also performed a null version of the same experiment. This time, after the 100th probe, some other low-level user authenticates. As you can see, the timing behavior of our following probes is unchanged, confirming our suspicions that the change in timing behavior is due to the atypical high-level login. These 2 experiments were run with timing taken at the method level. We ran an additional 3rd experiment taking client-side timing over a local area network to see if the timing side channel was observable. As you can see, the channel is now a bit obscured, but there does seem to be some change in the timing behavior of the probes following the atypical event. We were encouraged by this, so ran one more case study on the Apache Shiro library. We modified the same tutorial code, so instead of simply checking privileges, it also computed some non-trivial work. We then ran the same experiments as before. This time, after the atypical high privilege login occurs, there is a marked and sustained change in the timing behavior of the probes. This is visible over a local area network, and even we found across the public internet. We also performed 2 case studies on Graph, an open source navigation library similar to Google Maps. Grasshopper considers a source and destination and finds the best route between the two. In Grasshopper, when the source and destination are further apart than a certain threshold, different behavior follows. We assumed most queries would be between locations within the threshold, but that occasionally an atypical long-distance query might be made. Using these as our typical and atypical behaviors, we set up experiments analogously to those on Apache Shiro. Here, the timing behavior of our probes reveals quite effectively if and when an atypical long-distance query happens. This is certainly visible over a local area network, though the signal is somewhat diluted over the public internet. The final experiment on Grasshopper concerns whether or not the user chose to specify a non-default algorithm. We assume that most users would not choose to do so, but that atypically, a non-default algorithm might be specified. In this case, we observed a huge spike in the timing of our probes immediately following the atypical event. This spike is clearly visible even over the public internet and is on the order of tens of milliseconds. This is a huge contrast to the magnitude of the side channel in the password checking function that we observed earlier. Thank you everyone for coming to our talk. We have shown that just-in-time compilation can introduce timing side channels even into programs where paths appear to be balanced at the source code level. We have introduced a systematic way to learn information via these side channels and demonstrated that they are large enough in magnitude to be observable over the public internet.